Now 13 is an odd number. So 13 into 3, 39, plus 1, 40. So that is how you are getting number 40. Again 40 even number, it becomes 20. 20 even number, it becomes 10. 10 which is divided by 2, it becomes 5. Again 5 is an odd number. So 5 into 3, 15. 15 plus 1, 16. And that's how you are getting the last one. And because here you are getting 1, it will terminate, but not necessary that it will terminate for all the inputs. Always you will get the answer as 1. There may be a number for which you will never get the answer as 1, because you are multiplying a number when it is odd. So you are increasing the number when it is odd, and you are dividing by 2 when it is even. So no one knows whether this terminates on all the inputs. That no one can tell. So even checking whether a C program will halt or terminate is not possible to dig out. So this is the main thing in the computability. So these are the two issues with computability. That what problems can a computer solve? Can a computer solve every problem? Or it is not possible. What problems can a computer solve? Another example is checking whether a C program will halt or terminate is not possible to check. Now let us go to complexity part. We have already studied the subjects like algorithm analysis and advanced algorithm. So you are very well aware with this term complexity. How fast we can solve a problem or we can compute a function, and how much space do we require? That is a space complexity. So it is a polynomial time computable. Can we solve the problem in deterministic polynomial time like n square, n cube, n raised to 4, right? So that is known as a polynomial time computable problem. And another is non-deterministic polynomial time computable problem. So that you have already studied. Other are approximation algorithms. This also you have studied in your advanced algorithm, and randomized algorithms, randomized quick short. So all comes under complexity, the time complexity of these algorithms. So there are some functions that cannot be computed fast for our betterment, like if we consider internet banking password, then that encryption of that password should be very fast, because when you enter the password, it will be in the form of encryption transferred via the network. So encryption should be fast, it should not take so much time. But on the other hand, the decryption, if someone wants to decrypt that password which is entered by the user, then decryption should not be fast. The reason is, if someone can do decryption very fast, then anyone can again get back the original password. That's why we are going for 64-bit, even 128-bit encryption and decryption algorithms, so that we can have a better security. So example of that is RSA cryptography, right? And in the web applications, we require this kind of thing, that their password should not be decrypted fast. So you are very well aware with this thing, that we require fast algorithm definitely. In most of the cases, we are looking for an algorithm which can solve the problem in polynomial deterministic time. But on the other hand, there are some applications which require algorithm, right? So that computation cannot be done fast, right? So that is the requirement also. The next thing is, when we consider the main part, the automata part. So what problems can we solve or can we compute with a very little space, if very little space is given to us, right? What kind of problems can we solve, right? So constant space, we are using a stack as a memory. And what kind of problems we can solve, like a string searching, a language parsing, right? So searching a string, you might have done this kind of thing in your advanced algorithm, right? String matching algorithms like Rabin Karp and KMP and others. So what can we compute with a little space? So the automata, which is our main subject, automata theory, right? Our goal is we are given a very little space or sometimes no space, right? And what kind of problems we can solve. So basically we can say automata is a very small computer, the computer which we can say on a which we can draw on a paper, which can do a very small task, a small computation, right? And for that we are using a different automatas like a password validation. So that password validation itself is nothing but one example of automata. We can draw a simple machine. You have studied a little bit about this finite automata in your advanced algorithm, if you can recall, that you can match the string, you can find out a string in the given text if it is, if you create an automata for that particular pattern, right? So string searching through automata is possible. Language parsing, whether a statement is syntactically valid or not. When you write any programming language statement, you need to check, is it having a syntax error or it is not having a syntax error. So basically when you consider such kind of uh, example, it is nothing but we can say application of automata. Another application we can consider is when you are searching a particular file in your computer, right? When you search a file using your computer, you will find something like this dir command, dir star dot docx. So dir star dot docx is nothing but an example of automata. It is a small machine which does very small task, which does a very small task, and in which we require a very little space, right? Or sometimes we do not require any space at all, and we can solve the task. So basically, automata is a very small computer which we can draw on a piece of paper, and we can solve the small problems with the help of it. So you can see here the arrow, it is from automata to computability. So as we are moving from automata to complexity, it is more tough job. From complexity, when you move towards computability, it is the toughest thing under theory of computation. So basically this theory of computation having three main uh, stages: the automata, the base of theory of computation, then we have a complexity, how fast we can do, and then we have a computability, that can we do everything, can we compute everything through a computer. So these are the three main components in the theory of computation. So our focus will be on automata only, that how automata works and what is actually the automata is. So that is our main goal, right? Yes, one student has given that is a digital certificate. Yes, digital certificate is also a one kind of example which we can consider for the purpose of this encryption and cryptography, right? So the reason for slight noise is that other offline lab is also going on here. So you can see a mild disturbance because of that. That is obvious thing, right? Because there is an offline lab also here going on. So there might be small disturbance because of that for of some another subject. Okay, is it better now, or still you are getting this noise? Is it more clear now? Okay, so I think we can proceed further with this. So let us consider the simple example of computation, and then we'll go into a detail of automata actually. So here we have a simple example: fx is equal to x cube. So when you consider this fx is equal to x cube, what we'll write? how we'll solve it. So basically, our program will be like this. First, x is multiplied with x to get the answer of x square, and then finally this x square will be multiplied with x to get the answer of x cube, which is a simple step. So this is nothing but the program. If there is no direct function available to find the cube of a number, we can use this simple calculation. Find the square of a number and then multiply it with the number itself one more time to get the x cube. So here we can say if x is equal to 2, it is given to the CPU. Now CPU, as per the first statement of the program, it will execute the first statement. So 2 into 2, it will get the answer as 4. So now this 4, which is stored into a temporary variable, and will give the name that temporary memory as Z. So Z will be 4. Now after executing the second statement of the program, it is Z into X. So Z is your 4, 4 into 2. So that is how we'll get the 8, and this output will be displayed to the user. So that is how the computation will be done. It is nothing but a step-by-step execution of the statement. Right? Always we'll execute the statements in sequence. Definitely we have some if conditions and all that, but still we'll check that condition, and according to the condition we'll go to some another place. But always it will be a step-by-step execution. Always there will be a fixed path. We cannot say it is a random execution. You cannot execute the statements randomly. Always there is a specific purpose for that, and we are able to get that output. So that is how the computation will be done. So now when we consider the automaton, right? So this automaton is nothing but an abstract machine, and automata is the plural of automaton. So basically this automaton is an abstract machine, or we can say a robot. So basically when we consider the automata, we'll give the input to this automaton and we'll get the output. So basically this automaton consists of a central processing unit and the program. So memory, that is temporary memory, input memory and output memory, will not be a part of automaton. So automata includes only this thing, a central processing unit and the program memory. It does the calculation as per the program given in the program memory, and it will do the calculations, and output will be given to output memory. So automaton consists of CPU and the program memory only. So there are mainly 4 automatas, out of which 3 are part of your syllabus. A finite automata, which does not require any memory at all, without using any extra memory, any temporary memory, will solve some problems. And then we have a push down automata, so that is your stack, and we have a Turing machine, which is using tape as a memory. You might have studied about you might be aware about the audio cassettes or videotapes, which were normally used in the previous years, maybe around 10 or 20 years back. Audio cassettes and videotapes for recording of moments, right? People are using these devices. You might be aware with that. So basically that is nothing but one kind of a random access memory. Why it is random? Because you can have 2 options, a reverse direction and the forward direction, and you can go to any place and you can read the data from that. If it is an audio cassette or audio tape, you can have a reverse operation and you can play your favorite song. If it is at some another place, you can use a forward button and you can again play the song from that place. So actually it is a sequential memory. It is a sequential memory, a videotape, or we can say a audio tape, but still you have a random access possible through reverse and forward operations. Through reverse and forward operation, you can still have a random access of that a sequential memory, but it is a sequential memory, right? A linear arrangement of the memory. So when you want to understand this automata, normally I link this three automata with three different stages of our life. The first stage is when you look at a crawling baby. You might be, if you recall your childhood, you may be able to understand this very well. So when you consider a crawling baby, what is the limitation of that crawling baby? That crawling baby can go from one place to another place within a room, or maybe it can go from one room to another room. That is the limitation. Nothing he can do more than it, because he is at a very small stage, maybe 2 or 3 years. We can say 2 years, 1 and 2 years, between 1 and 2 years, right? Because after 2 years, he can walk. But still, we can say that even 2-year-old boy or son, it has certain limitations, that it can walk in the room, it can walk in the house, nothing else, nothing more he can do at all. So basically, uh, we can say this the basic stage. At that point of time, what parents will do, parents will give them a vehicle, so that he can enjoy his childhood. So basically, normally they will give them a vehicle like a tricycle. A tricycle is the first vehicle which you have always used, right? So that tricycle is we can say, a one kind of a finite automata. This finite automata is, we can compare with a tricycle. It has very limited capabilities, right? It has three wheels, one in the front, two at the back. The kid become very happy, and he will try to use that cycle to go from one place to another place in the house as fast as he can drive. He will do that thing. And most of you have done also in your childhood, yes or no? You might have done this, yet you can still recall your childhood, and you can recall your tricycle, right? So it has a limitation, but you became happy at that time. Yes, I am on the top of the world, and this is a great thing which I got from my parents. And now I can go from one place to another place, anything I can do. And with as much speed as much you can achieve, you will drive that tricycle, right? So that is nothing but a finite automata. It has a very limited limitation. What is the limitation in it? That when you use your tricycle, when you enjoy your childhood, you observe that some of your neighbors, having some of your friends in your society, they are around 5 years old, 5 or 6 years old. They are not using this tricycle, right? They are using their bicycle, small bicycles they have, and with the help of that bicycle, they can go from one friend's house to another friend's house. So you feel that yes, my tricycle is very small. Actually, with this tricycle, I cannot do all the things. I can just move here and there in my house. So now I think I should improve my vehicle, and you will tell your parents, yes, now this tricycle is not good for me. It has very limitation. I cannot even go from my friend's, cannot go to my friend's house with the help of this tricycle. So I want a better vehicle, because now I am a 5 year old. So I need a vehicle like a bicycle. So your parents feel that, yeah, it's true. Now you cannot go to your friend's house with the help of this bicycle. So now definitely we should give him something more, which is better, which has more power, more capabilities. So you will get your bicycle from your parents, and with the help of that bicycle, what you will do? It is a small bicycle. What you can do? You will use the bells which is associated with that bicycle. You will you pedal as fast as you can, and you will go to your friend's house, which is in the neighborhood, maybe 2 or 3 house away from your house. But with the help of bicycle, you can do that. Even you can keep some of the small books and color boxes also with you when you go to your friend's house, and both of you will do some coloring task and everything, drawing task and all that. So we can compare this bicycle as with push down automata. The push down automata with bicycle I am comparing, the reason is it has more capabilities as compared to a tricycle. Tricycle is only helpful in the house. You can only do a very limited thing, right? And nothing more than it. So we can say tricycle is nothing like a finite automata. No memory is available, no capabilities. You can do a very small things with it. On the other hand, this push down automata, I am comparing with the bicycle. That yes, you have more features available. You can ring the bell, you can have pedals, you have cycle stand, and you can go to your friend's house, right? Which is in the nearby society, or maybe 2 or 3 home away from your home. So it is your bicycle. So which has some more capabilities. So that is nothing but your push down automata. So push down automata is also a computer which can do some more tasks, more interesting tasks as compared to a finite automata. So basically, in finite automata, you will solve a very small problems, very simple problems. With push down automata, you can solve some more complex problems, more interesting problems, right? Which requires a comparison and other parameters. Because in case of finite automata, you cannot do any comparison. You cannot tell even that whether two things are equal or not. While in case of push down automata, you can do a lot of comparison. So you have more capabilities similar to a bicycle, right? Now further, what will happen when you reach to 8 9 standard or maybe 10 standard, you feel that this bicycle is taking so much of my time. I want to go for tuitions for my subject, and now this bicycle is wasting my time. I have to do so much pedaling, and I need some vehicle which has more power, which is fast, so I can utilize more time. I can go to my tuition classes very well, right? And I don't want to waste my time, right? And you don't like the your own bicycle, right? And you will expect from your parents a better vehicle, right? So that you can go to a tuition class, you can save your time. You also want to enjoy the speed. Now you understand what the speed is, how, and for that you need a better vehicle. So definitely you will look at your parents, and parents will understand your need, and they will give you the more powerful vehicle. So you have started your journey with tricycle, you have used bicycle in between, and you have reached to now the third vehicle of your life. That is your any two-wheeler. I think you have gone through this journey, most of you. Yes or no? Okay, so only two people out of 60 have enjoyed this kind of journey from tricycle to bicycle to two-wheeler. Yes, so most of you have done this, right? Okay, so I think I should tell now. All of you have gone through this, right? Because otherwise, this responses will be 60 exactly. Okay, understood that now. Fine, good. So basically, all you are listening very well. So the point is, when you are getting your vehicle, which is your two-wheeler, maybe your Activa or bike, whatever, or maybe you will have your own vehicle, which is more powerful, like which is having a very high cc parameters, like 120 cc and 150 and 125 cc or 150 cc and all that powerful vehicles, right? So basically, it is, we can say, a more powerful machine which can help you to reach from one place to another place in your city. You can use that two-wheeler to your tuition classes, to your friend's house. You will visit nearby, we can say, a shopping market. You will use that in the city normally. So it is a more powerful machine. So definitely, with this more powerful machine, you can do more tasks, more complex tasks. So finite automata is your tricycle, we can say. Push down automata, more powerful, is your bicycle. We can go for one more level, which is not in your syllables. It is known as a linear bounded automata. The third level is known as a linear bounded automata, right? And we can say that this your two-wheeler is nothing but your linear bounded automata. Now still you feel that we want to solve more complex problems, more and more, because we are using a computer. Right now we are using a computer, right, which is solving almost every problem, not 100%, but it will solve all the problems which are of daily need. Computer is used in every field nowadays. So we want to solve a very complex problems. This is also a very complex problem that we are attending a meet. You are at your home and you are able to listen to this lecture. So it is also a very complex problem which is solved by the computer with the help of this meet like an application. Right? This is your VoIP example. So basically, we require more and more powerful machines in our to solve our requirements, and our requirements are changing frequently. So still we can say that if you feel when you get your job, right, when you get your first salary, what you will dream? You will dream of your car. You will have a dream of your own car because you feel that with the help of my two-wheeler, Activa or whatever bike, whatever you have, right? You don't prefer to have a long drive, right, on a beach or somewhere, right? You want to go from one city to another city, nearby city. You don't prefer a two-wheeler like bike. If you want to go for a long drive, you want a vehicle which is more powerful, more comfortable, right? Uh, so that is what we can say. That is our requirement, a future requirement. So we can say Turing machine is something like that. Turing machine is nothing but our real computer, a computer which is known as a Turing machine. So we can say the technical name of this computer which we are using, our laptop, is the Turing machine. That Turing machine does everything. It does everything. It can solve any problem. How it solves the problem, right? Suppose, let me give a simple example to understand this. That in case of Turing machine, suppose I want to play a video MP3 file. So now, can I use a Microsoft Word to play the MP3 file? So answer is definitely no. You cannot use Microsoft Word to play the MP3 file. The reason is that when you open the Microsoft Word, your Turing machine behaves as a word editing software. How your Turing machine behaves, how your computer behaves, it expects that you are giving some text as input, right? It is not having a knowledge or rules related to how to play the MP3 file format. So that's why sometimes you are getting the error, right? So you cannot play the file with your Microsoft Word, which is an MP3 file, because when you are loading the program into your main memory, so according to the rules which are given in the program, your Turing machine behaves. Turing machine is nothing but you have to tell the rules, you are getting the output accordingly, right? We itself are behaving like that. A simple example is that right now I am speaking in English. You are able to understand because you know the rules of English language. You know the English grammar, right? You know the Hindi language. You know Hindi grammar. You know English Gujarati language. Most of you and Gujarati grammar. So you can understand these three. Now, if there is any another expert who will come to our college and he will give the speech in the native language like Tamil, Telugu, right? Then what you will do in that expert talk? Can you understand anything? The answer is no. We cannot understand anything. The reason is because we are behaving like a machine. Right now, in our machine, in our brain, the installed softwares are for three languages, maybe for most of us. That is English, Hindi, and Gujarati. So we can understand that three, and we are able to extract the meaning from it. But if a new person from Tamil Nadu will come and he will speak his expert talk in Tamil language, then none of us will understand anything from that. The reason is we have not installed that, right? Kind of grammar or software in our machine, in our mind. So we cannot process that thing. The same thing is done by our Turing machine or our computer. Suppose you want to play the MP3 file, and if you open the Microsoft Word, definitely it will not be played. The reason is there are no rules loaded into the machine at that time because you have opened the application Microsoft Word. So computer understand that right now you are dealing with Microsoft Word, right? You are dealing with a Microsoft Word. So that rules are there in the computer at that point of time. So according to that rule, computer cannot play the MP3 file. Reverse scenario is also there. Suppose you open a software like media player, any media player software you open, and in that you try to open the doc file, Word file. What will happen? you are not able to do that, right? So the reason is at that point of time, the rules for media player is in the computer, in the main memory. You are using that application. So according to that application, it has nothing mentioned in it how to handle the doc file. So it will stop. Sometimes you might have gone through an error. Uh, you have to install a required codec, right? You have to install the necessary codec to play back this audio file. Have you gone through such errors? Right? So what is that codec? So that codec is nothing but it is a one kind of set of rules. Our program, that codec is nothing but a set of rules. If you specify the rule, your computer will understand that rule, right? And computer will behave accordingly. If you do not specify a necessary rule, then without rule, your computer cannot do anything, right? Suppose just I'm giving a simple example. You will you will associate one kind of uh, uh, machine which gives a shock to a person, right? Suppose assume that you have one hardware when someone will touch that machine, it will give a shock treatment to another person. And if you install that rule, then what will happen? If other than you, right, will touch your laptop, right? So it will give the shock treatment to that person. So that is what how the computer will behave like that. Why? Because you have installed that kind of rules. That if you are the person, right? If you are the person, definitely it will recognize you and you will not face the shock treatment. But if unknown person will touch your laptop, he will have a shock treatment immediately. He will get a shock, right? So you can install that kind of hardware and you can do that kind of coding. So computer will behave like that. Yes or no? So that is what the computer does. You have to just specify the rules, and according to the rule, our machine will work. So Turing machine, our real computer, is based on that principle. Whatever task you want to do, you need a set of rules for that. Right? Set of rules means we can say a software, application software, we can say, or a system software. So we need Windows. Without Windows, can you use the machine? No, it is of no use. Why? Because that is a system software. That is a system software, and according to the system software, your machine behaves. So you have to specify the rule. As per the rule, your machine does the thing. Without that, it cannot do anything. So this Turing machine is giving the same principle. You give the rules, and according to that rule, the machine behaves. So your machine is just like a black box, right? You give the input. Now in the black box, if there is a MP3 uh, uh, rules are there, then you will able to play the song. If the rules for word file are there, you are able to do the editing task. If in your black box there are no rules for a given input, your machine will not behave and it will not give any output. It will halt in between. It will halt. Definitely it will halt. It will not do anything if no rules are specified for a given task. So that is how we can define this Turing machine, or we can say our real computer. I hope now it is clear. Yes, this Alan Turing has defined the concept of a Turing machine, and this Alan Turing is the founder of, we can say, our computer, right? The real computer, which is based on this principle. You define the rules, encode the rules, and according to that rules, the machine will behave. If I will give a rules of addition, my computer will do the addition. If I specify a rule for square root, my computer will calculate the square root. If no rules are given for any task, computer cannot do that task at all. It is not possible for computer to do that thing. So it is a very obvious thing. So basically, we can say this finite automata is your tricycle, very limited memory. You can do a very small task like string matching. Push down automata, we are using a memory more powerful like bicycle. We'll use extra memory as a stack, and we can do a comparison, and we can say syntax validation. We have a syntax rules, and we can validate that syntax statements as per the syntax using push down automata. So basically, when you consider HTML like a language, so we have input tag, HTML, closing tag, and the opening tag. So basically what they are doing a matching, right? So that kind of thing will be done by this push down automata through a stack. So we require this kind of machine for that. So we can compare that with your bicycle. Then your two-wheeler, we are comparing with your linear bounded automata, which is not in your syllabus, the third level of automata, a linear bounded automata, in which we are using a fixed memory, fixed random memory. We are considering a fixed size random memory in linear bounded automata. And in Turing machine, we are considering infinite random memory. In case of Turing machine, we are considering the infinite random memory, and we'll compare that with a real computer, the highest powerful machine. We can say your four-wheeler or your dream car, which is more powerful, more capable to do any task. So that is how we can consider the Turing machine. So I think these four automatas are clear to you, that what these four automatas are there, what are their different capabilities. And the Turing machine, the highest one is the real computer. Okay, basically quantum computing is a different scenario. It is not, we can say, automata. It is one kind of it is a group of Turing machines, right? So basically we can say it is a group of Turing machines, right? That is what this cloud computing and all that, right? But it is not a different kind of automata. All are Turing machines. So cloud computing is what? It is a group of these Turing machines which is doing a task together. They are doing the task together. All this cloud computing and all, right? They communicate with each other and they are doing the task, right? That is how this cloud computing works. You will have one specific task, a very big task. So you will associate some task to one Turing machine, one computer, another part of that task to another computer, and together they will work on that task and they will give the solution. That is how the cloud computing works. It is nothing but a group of Turing machines, right? It is a group of Turing machines that collectively they are doing this task. So so when we consider this finite automata, we don't have any memory, as I said, right? It has only input and it will produce the output, whether it is valid or not. So example of this finite automata we will consider as the vending machines, or when you visit any shopping mall nowadays, you will find automatically door will close and open. When you reach close to the door, automatically it will sense, there are sensors for that, that will sense that person is close to a door and door will automatically open. So it is an example of finite automata. It doesn't require any memory. It does not remember anything. It will just open the door. A vending machine is another example. Your switchboard, right? When you use a switchboard on and off switch, it is your example of finite automata. Finite number of states are there in it, right? So basically in your syllabus, there are three chapters, chapter 3, 4 and 5. There are three chapters, 3, 4 and 5. Basically, they are related to a finite automata in the book, which is Johann C. Martin. The book is Johann C. Martin. Right? It is Johann C. Martin. It is a third edition, right? And chapter, they are finite automata. Chapter 3, 4 and 5, they are finite automata in the Johann C. Martin. So which is a part of your syllabus. Now, along with that, other automata which we know, that is a push down automata, in which we are using a memory as a stack. So as I told, right, compilers, right, syntax checking. I given an example of HTML tags. So syntax checking, right, is done through this push down automata using a stack like a memory. So it is known as a push down automata. It is more powerful as compared to of finite automata. And related to this, in your textbook, there are chapters 6, 7, and 8. It is from John C. Martin, same book. There is no better book. There is no better book for this subject. So we have to strictly follow this one book, right? No reference book is also required, right? So this is the only book we are following in this subject. And this definitely a subject that if you understand this subject, it does not require any preparation before your exam, right? It does not require any preparation at all. If you understand the subject, you can attempt the paper fully and you can score 36 out of 36, right, without any preparation. And if you don't understand the subject, right, then even though you will work for 12 hours a day before your exam, you may score 0. So every example is different from the previous one. Each and every example is a new example. So it is not like that you solve one example and you are able to solve other similar examples. It is not possible in this subject, right? And each chapter having an exercise of around 400 examples, right? There are 400 exercises. There are 400 exercises in each chapter. So definitely you cannot solve all, but you will solve the most important one exercises, which will be helpful to you in the GATE examination. So each and every example is different. So if you understand how to solve, what is the method to solve these examples, then and then you can solve new examples in the examination, right? Because there will not be a repetition. Two examples will not be equal at all. So the important exercises we will cover during the lecture, so you can understand how to solve the exercises of different type, right? And we'll have sufficient good practice in each chapter, so you don't have to worry about that. But keep in mind that you cannot mug up. There will not be a block diagram. So draw the block diagram, write a short note. That kind of questions will not be there in the subject, right? You don't have to draw any block diagram at all. You don't have to write any short note at all, right? So don't worry about that. You have all the new examples, all the problem solving exercises, and if you solve it, you will score the marks. So Turing machine having a random memory, more powerful, it can solve any problem for which you can write the algorithm. So that's why I have used the word any algorithm. The focus is on any algorithm. If you can write an algorithm, a deterministic algorithm, if you can write, then it can solved by the Turing machine. That is your real computer. If you cannot write an algorithm for a given problem, your computer will not help you. It cannot solve that problem at all. So I hope it is clear. It is the most powerful thing. So you can see the power. Finite automata, very less power. Push down automata, more power. Highest power, Turing machine, which can solve more complex problems. The finite automata can solve very small problems. Turing machine can solve very complex problems. So another important term, that is a formal language. Because theory of automata, I think you know very well what is theory of automata. Another important term is the formal language. So this formal language we'll see in detail in the next lecture, because this is the actual subject, theory of automata and formal languages. Okay? It is theory of automata and formal languages. So we have understood what is automata, what is theory of computation today, and we'll see more about these formal languages in the next lecture. I hope you are understanding the things. Types of automata is clear. Which memory is used by which automata, I think it is also clear. There is no doubt in this, right? So thank you all. I am ending this session now.